This lecture will help you to understand simplex method, and in this lecture I am going to explain the steps to be covered to solve the simplex method with a brief introduction. Well, the simplex method is widely used linear programming problem technique to give us a solution for linear programming problems. And we better to know where we should apply simplex method, and also I have given a series of lectures on graphical method also. Graphical method can't be used for problem involving more than two decision variable. Graphical method limited for only two decisions variable because in the graphs we want to point out 2 points to make join that axis in the graph. So when you have more than two decisions variable, there are some methods based on the concept of slack variable. If you have more than two decision variable, the solution will be given through slack variable. In the slack variable, we have trial and error method and simplex method. But trial and error method is extremely cumbersome and very time consuming for calculation, and from trial and error method, successive solution may not be culminated into the optimal one. For that we use simplex method. So simplex method is an improvement over the trial and error method, and it overcomes the deficiency involved with trial and error method also. In this lecture you will understand steps to solve the simplex method. Then very briefly let us understand what is simplex method. As I told you already, simplex method is an improvement over the trial and error method which covers the deficiency involved with the trial and error method. So usually in the simplex method we will give solution through initial simplex table. If you are unable to have a optimal solution in initial basic feasible solution, we have to initiate some more adjacent vertexes. So it is an iterative optimizing technique, which means we will give solution through many iteration, where first we will find an initial basic solution which is called usually vertex, and then if you are unable to find as an optimal solution in the initial basic solution, we will proceed to the adjacent vertex, and we will be continuing from one adjacent vertex to another adjacent vertex till an optimal solution is attained. So it means simplex method, in the simplex method we will give solution through iteration by leading iteration until we attain optimal solution. So we better to understand the steps to be followed while we are giving optimal solution by the simplex method. Since it is a very important problem, I am going to make a separate video for steps to be followed for computation of simplex method. Firstly, as we know, we have to express the problem, real world problem in mathematical formulation, and suppose we have to maximize or minimize z, a linear function, and the basic variable we will consider x, y, z, like that x1, x2 till xn are basic variables. Those variables must be in objective function. So then if you want to express the basic variable in objective function, z, example z maximization equals to c1 x1. Here c1 is the cost coefficients of decision variable. It means cost is associated with x decision variable, and it goes on continuing like that, c2 x2 plus cn xn. This is the first equation we have to follow. If you come to this side, subject to constraint, how do we treat subject to constraint in the simplex table while we are making a mathematical formulation is, these are a11, we will derive this from subject to constraint a11 and x1. x1 is, as you know already, it's a decisions variable, and a11 is a cost of respected decision variable. So a11 x1 plus a12 x2, and it goes on a1 n xn lesser than or equal to b1. b1 is simply a set of constraints. Since it is a first constraint, we are giving 1 1 1 1. If you move to the second constraint, we will give 2. So treatment of second constraint would be a21 x1. x1 in the sense decisions variables will remain same for all the constraints. So a22 x2 plus a2n xn lesser than or equal to b2. So second constraint b2, and you can take too many constraints like that. At the end we will end up this am1 x1 plus am2 and so on amn xn lesser than or equal to bm. So also we have to express linear non-negatives. So you know that xj greater than or equal to 0. For j1 2 3 it could be j1 2 3 until n. So here, as I told you, c is a a coefficient of decisions variable. Cost is associated with decisions variable, and aij b m into n real matrix, and it means cost matrix of coefficient constraints, and b1 b2 until till bm be a set of constraint in this example. So firstly we will make a mathematical formulation of the given real world problem, then we will move further. So second step, we have to convert LPP into standard form of LPP by adding or subtracting slack variable. As we know, simplex method is superior than graphical method. Why? Because we will convert LPP into standard form of LPP. If you convert into standard form of LPP, it gives a standard procedure for giving solution in LPP. That is why simplex method is superior than graphical method. So you can watch my another video on standard form of LPP, where I have detailed how to convert general linear programming into standard form of LPP. I will brief here to make you better understand. So we have already formulated mathematical formulation made for maximization, subject to constraint, and non-negatives in the earlier slide. Adding to that, so here based on the constraint, we have to add or subtract that slack variable. Say for example, in the first constraint we have added 0 s1, and it means slack variable 1, because here it is a lesser than or equal to type, so we have added. And as you know already, in the standard form of LPP, the equation subject to constraints must be expressed in equation. So we have removed lesser than or equal to type, and right side of constraint must not be negative, it must be positive. If it is negative, we will multiply by -1 to make positive. So this is a subject to constraint. I have considered all the subject to constraint. First subject to constraint, I have added slack variable. Second also I have added slack variable. Until as many as subject to constraint we go on considering, we will add slack variable. Immediately after adding slack variable in the subject to constraint, we also should express that subject to constraint in objective function, because this is also slack variable, slack decisions variable. So this must be in the objective function. Not only in the objective function, also we have to express the in the non-negative. So xj greater than or equal to 0, j in the sense decision variable 1 2 3 until n. Also for we are also expressing the slack variable, that is si, for all I is equal to 1 to m. So in the sense, the objective function is fourth equation, and subject to constraint is fifth equation, and non-negative or sixth equation. So this is how we will convert LPP into standard form of LPP. Unless you convert into standard form of LPP, you cannot give a right solution in the simplex method. We are going to give a standard procedure for LPP, so we have to convert into standard form of LPP. After converting into standard form of LPP, you can directly fill those information in the initial basic feasible solution, simplex table. So this is the format. It is not a typical format. The format changes from author to author. I have considered IGNO material for giving lecture. So it's a format to give a solution. Firstly, concentrate CJ. CJ are C1, 2, 3, 4, 5 like that, and these are decisions variable. These are coefficient of decisions variable. Decisions variable 1, 2, 3, and lastly slack variable. It is also going to be continued. And here we have to consider basic variable. Basic variable in the sense, here we have to consider slack variable, and it is a profit or units a coefficient of basic variable. Coefficient of basic variable slack variable values, it has no value, it has 0 value, so we have mentioned 0 value. In case when you remove this slack variable and insert some other addition variable, it coefficient cost will come to this point. And quantity, as you know already, quantity will be available inside of constraint. If you want to know, look at here, this is a quantity and this is a slack variable. This 0 is a slack variable profit or unit, and C1, Cj are C1, C2, C2, 3, 4 and X also there. So this information we are going to put in the initial simplex table. So here we have A11, the subject to constraint cost matrix we will mention here, and here in the S1 we have one value, so I have mentioned value 1, and in the first slack variable for S1 there is a value, in the second slack variable for S1 there is no value, but for S2 there is a value because we have introduced to second constraint, so we will give to the respected second constraint value. So in this vice versa, there is no value for slack variable first, there is no value for S2. We will just express the values here. These are xj, and here you can see z maximization, z is optimization. Here we will have two things. One is zj you can take like by multiplying this value to this value. Say for example 0 into this plus 0 into this plus 0 into this, and so on. You will go on like that. Sorry, if you want this value, x1 value, 0 into this and 0 into this plus 0 into this, you will get this value. If you want x2 value, 0 into a12 plus 0 into a22, you will get this value. So this is how you will find the values of this zj. So after finding zj, you will subtract Cj by Zj. What is that Cj? Here it is a Cj. By this value, you will subtract this value. So Cj Zj, you will get this value. Okay. So you will also have to find a replacement ratio. Replacement ratio you will find after finding Cj minus Zj. And there is a condition to give an optimal solution. Condition is Cj minus Zj must be lesser than or equal to 0. If it is not so, you will go for another iteration. So one thing is clear, you can have solution in initial simplex table also. If you are unable to find an initial simplex table, you will lead through another iterations. As I said if the Cj minus Zj is lesser than or equal to 0, then it is an optimal solution. If not, what to do? Okay, let us look into that. So that we will check the optimality condition. As I told you already, if all the Cj minus Zj values are lesser than or equal to 0, the solution under test is optimal. You can stop the giving procedure for this. If not, if at least one value of Cj minus Zj is positive and corresponding to the most positive Cj minus Zj, all the elements of the column xj are negative or 0, then this solution is unbounded. I will show you what it means. So if Cj minus Zj is lesser than or equal to 0, you can stop procedure here because you reached at optimal solution. If at least one of the value of Cj minus Zj is positive and corresponding to this positive value, positive Cj minus Zj, all elements of xj are negative or 0. Example, Cj minus Zj is not 0 or negative. It means all the table values, that Cj minus Zj values, must be lesser than or equal to 0. If not, if any one of the Cj minus Zj value is positive, say for example this C2 and B2 is a positive, this value is positive, and corresponding to this value, these values are negative or 0. Negative or 0, then you are unable to find a replacement ratio. Okay, you will lead one more iteration by finding replacement ratio. If you want to find the replacement ratio, you want to find this value. So one thing is clear, Cj minus Zj must be lesser than or equal to 0. Okay, then you are arrived at optimal solution. If Cj minus Zj are positive, select the most positive value. This is, I assume this is the most positive value corresponding to these slack variable value, these variables value are negative or 0. Then it is a unbounded solution. You cannot give solution for this kind of problem. That is what I am going to tell. So this is unbounded solution. Okay, one thing in either the two cases you will stop procedure. One, when the Cj minus Zj are lesser than or equal to 0, all the Cj minus Zj are when there is a unbounded solution. Okay, otherwise there is a only one value, the positive, then how to treat that value. Okay, you can refer to the third point for that. Suppose at least one value of Cj minus Zj is positive. In the initial simplex table, in the Cj minus Zj, one value is positive. Suppose the most positive value is say C2 minus Z2, and at least one entry in the column Xj is positive. Then the optimal solution under then solution under test is not optimal. You want to improve that solution. One thing is clear. Suppose at least one value of Cj minus Zj is positive. Suppose the most positive value is, suppose assume C2 minus Z2 is a most positive value, and at least one value in the entry, one positive value in the entry Xj is positive, then the optimal, it is not optimal solution. You want to improve that solution. I will show you how it works in the initial simplex table. Look at here, this Cj minus Zj is not 0 or lesser than 0, and C2 and B2 is a most positive value, and in the C2 B2 any one of these value is positive, any one of these value is positive, then you are not arrived at optimal solution. You want to improve that solution. Then how do we improve that solution? Let us look into that. So it means you are not arrived at optimal solution. You want to improve the solution you obtained in the Cj minus Zj. To improve solution, you want to go through these points. Okay. Firstly, you want to find the replacement ratio. After finding the most positive value in the Cj minus Zj, so you will find out the incoming variable. But after finding incoming variable, you will find replacement ratio. So how to obtain replacement ratio? I will tell you how to get the incoming variable. Suppose C2 minus C2 X2 is the most positive value you found out in the Cj minus Zj, and then this value will be incoming variable. The value corresponding to this, that is a X2 is a decision variable. This decision variable will be incoming variable to the next iteration. It means any one of these values will be outgoing and this X2 will incoming. Okay, so after finding this incoming variable, firstly you have to identify the most positive value. Say for example C2 and X2 is a most positive value. The value, the variable corresponding to this value is an incoming variable for next iteration. And now how to find replacement ratio? Replacement ratio will be found out by dividing quantity into respected value. Respected value means the value you marked in the most positive value. Say for example B1 divided by A12 will be value for here, and B2 divided by A22 will be value for here for replacement ratio. So now you also found the replacement ratio. Now you want to find outgoing variable. Say for example in the sum of the example you have only two constraints. So two constraints only can allowed here in the basic variable. So firstly we considered a slack variable. So when X2 incoming variable for next iteration, any one of these basic variable must be outgoing variable in the next iteration. To find out outgoing variable, we will go through replacement ratio. In the replacement ratio we have to consider lesser value, which means least positive value. If there is any negative value, you are not going to consider that negative value into this. It means you, out of the positive value, you want to prefer least value. Then least value will be outgoing variable in the next iteration. Then instead of S2, X2 will come. That is how you will find least positive incoming variable, outgoing variable, and replacement ratio. And also you want to find out the key element here. So you have marked like this, because it is a outgoing variable, and most positive value incoming variable also you marked here, and you will mark like this. So here this value intersected at this point, that is A22. This is a key element. Key element you will get at the intersection of this marked value. Okay, so that is what I was saying. Incoming variable is the xn be the variable which corresponding to the most positive value in the Cj minus Zj. Find out the most positive value. In that corresponding xn value will be incoming variable. And replacement ratio, we divide the value of quantity by the corresponding positive values in the column, in the xn column we found in the incoming variable. So after that you will find a replacement ratio. In the replacement ratio you will select least positive value to remove the one of the variable in the basic variable. So that is outgoing variable. To remove outgoing variable, select the minimum replacement ratio. In the replacement ratio, select the minimum positive replacement ratio. Do not select negative replacement ratio. And as I told you already, key element is the, we will get at intersection of column and row. Intersection of the row corresponding to the outgoing variable and the column corresponding to the incoming variable. You will get some intersection to the column outgoing variable and incoming variable. Then this value is a key element. After that we will find unity by key element. We will convert the key element to the unity by dividing all entry, and also we carry a suitable operation for on each row, and using the row containing key element. Using key element we will carry a suitable operation for the row. That you will come to know while we are calculating the problem. And you found out replacement ratio, incoming variable, outgoing variable, key element, and you carry out a suitable operation for row using key element. You done everything, and also at the end you want to check the Cj minus Zj value. Then also it must be lesser than or equal to 0. If not again you want to lead for one more iteration, and we will repeat the procedure until either an optimal solution is obtained or there is an indication of unbounded solution. So by these steps you can find a simplex problem solution. Thank you so much for watching.